So welcome back, everyone. Hopefully your stress levels have lowered somewhat, or at the very least, you are looking for a welcome distraction at this point, and that's what hopefully this class can be. I've gotten some questions on the midterm. One that seems to be cropping up with many students is the question about the initial conditions. That might have been worded confusingly. One of them I gave to you, and the other one I was just trying to say that at time 0, the horizontal displacement is 0. So there was a question of kind of starting at rest and what does that mean and so on. That's one point. A second point is, I think that universally, every time we do this problem, the hardest part for students is finding the right characteristic timescales and length scales. And what you might find is that all your characteristic timescales and length scales have mass in them. One thing I might suggest doing is recognizing that this looks like it'll be, well, actually, the first thing I would say is I picked this problem because it is conceptually fairly straightforward. It's something that you should have some intuition for. It's a mass on a spring, you're going to hit it, and it's going to do something. And I would like you to go through the thought process of, if the mass was really large and the damping was really small, what do I expect y as a function of time to look like? Just draw it out. And then do the opposite. Say, if the mass is really small and the damping is not small, and I hit it, what do I expect the deflection to look like? You should be able to sketch these curves out. And the sketch of these curves will kind of help guide your modeling in terms of recognizing that this might be a singular perturbation problem. If so, it might make sense to try to find your characteristic time scales and length scales kind of away from that initial time scale. If it makes sense to find those away from that initial time scale, what you might do is then to say, if I sketch my drawing, I think there's a boundary layer. Is that boundary layer near 0? If it is, then I would expect my characteristic time scales and length scales to be not the one in that singular region, but the one in the regular region, the one that's kind of not only happening for that instant in which you hit the thing. So what that might mean is consider the reduced problem, check your pi groups and see if you can find your characteristic length scales and time scales from that reduced problem. That might help you remove mass from those characteristic values. Mass obviously is going to be an epsilon. It's the small thing that's going to make up epsilon. But I think a lot of people are getting tripped up with finding the characteristic length and time scales. And I would just say, if we know that the characteristic length and time scales, as I've said in the problem, should be of order 1, otherwise they're not characteristic of the problem. So I'm going to say that point again because it's really important. Your characteristic time scale and your characteristic length scale should be of order 1, otherwise it's not characteristic to the problem. So that should help you kind of think through the process. And with that in mind, and if you go back through our notes, we kind of did that for, in particular, if you look at like the problem we did with like weak diffusion or weakly nonlinear, I think it was the KPP problem. You could see that like the characteristic time scale of that problem was different depending on kind of what was the small thing and what was the large thing. And that's the same case here. We want that characteristic time scale to be of order 1. So I would consider the reduced problem in which that term that is multiplying the mass goes away. Can you find the characteristic time scale and length scale on those problems and see how that rescaling works? The point of that initial process of sketching out what you think is going to happen is going to be the way that you determine if you're on the right path, if you're on the right path to solving it. Because Mathematica can solve this problem analytically no matter what. However, if you calculate epsilon wrong, you're going to get a different solution. So the problem is not necessarily solving the differential equation, it's making sure that you have the right differential equation, at least to start the problem. So those are some of my advice to you as you're getting started on this, but they're kind of general advice as well. If you're starting a mathematical modeling problem, what do you expect the behavior to be? Can you predict what you think is going to happen? In this regime, it should be like this. In this regime, it should be like this. Are there going to be undamped vibrations? Are there going to be overdamped vibrations? Is it going to be, you can kind of game this out however you want, but those are my thoughts. Any questions on the midterm? Nothing? All right. Pretty straightforward, hopefully. Okay, so if there's no questions in the midterms, we just wrapped up with the second section of this course, which is on perturbation methods, which is to say that if we kind of just zoom out for a second, the first section of this course was really understanding kind of how to create comparisons, how to scale variables. So that way we're looking at comparisons for variables as opposed to the raw variables themselves. How do we take an equation and write it into a non-dimensional form? I think that motivation might hopefully is clear to you now, but it might still not be. But that non-dimensional form allowed us to have a small parameter that we could then use to help approximate solutions to problems that were hard to solve. And in some cases, not possible to solve analytically. That small parameter is not going anywhere. So we're going to be continuing kind of using the idea of a small parameter as kind of the fundamental concept, in a sense, for this next section. But if you think about it, what we did at the beginning is we said, like, okay, you can use the dimensions of your problem to come up with a toy model. In the second section, we built on the fact that we could use the dimensions of the problem to get a dimensionless quantity and a dimensionless set of equations. And then we could use the fact that generally something is small in your equations. We could use that fact to approximate the solutions to those equations. The next part of this talk is in a way, how do we kind of derive the governing equations from a general principle that kind of underscores all of physics. And that general principle is what's referred to as the principle of least action. I'm going to come back to that in a second. But before I dive into the principle of least action, this topic, what we're going to be working on next, is referred to as the calculus of variations. And it is useful hold on. The next topic we're going to cover is the calculus of variations. And the underlying mathematics here are useful whenever you need to find some extreme quantity about a problem. What is the shortest distance between 2 points? What is the fastest, what shape would allow a ball to roll fastest down a hill? What is the shape where if the length is fixed, if I draw a shape on the board in 2D, what is the shape that will enclose the largest surface area? In the case of questions relating to physics, we kind of know, hopefully, the idea that things tend to minimize their potential energy. That's what we hear all the time in solid mechanics. But even bigger than things tending to minimize their potential energy is this broader idea that there is a principle of least action that says things tend to minimize not only their potential energy, but they tend to minimize the difference between their kinetic and their potential energy. They want to have the smallest amount of action, where the action is that difference between the kinetic and the potential energy integrated between 2 points in time. And the goal is that the resulting behavior we see in a system is going to be whatever minimizes that action. This idea of minimizing, maximizing, extremizing reminds us of ideas from calculus, right? I have a function and I need to extremize that function. What do? I take the derivative of that function with respect to the independent variable, and I set that derivative equal to 0, and I find the extremum. That's calculus. The problem gets a little bit more complicated when what you're trying to extremize is not a function, but it's a function of a function of a variable. We're going to talk about that. A function of a variable is what's referred to as a functional. And the calculus of variations deals with extremizing functionals. We use calculus to extremize functions and the calculus of variations to extremize functionals. So let me write that down. Function of a variable. What's an example of that? So we might say that if I'm holding a ball up in the air, the potential energy within that ball depends on the vertical position of that ball, which depends on time. Because if I let go of that ball, the vertical position is changing. So let's think about that. We can call that the potential energy V, which depends on the location of my ball, which we can call x, which is some vector. And x, in this case, let's take the example of just a simple ball in the air that might be falling. That position of that ball depends on time. So the potential energy is a functional. It's a function of position, which is a function of time. Times are independent variable. X of t is a function. V of x of t is a functional. I'm going to clear things off here for a second. Let's see if we can move this down. So for a function, we know how to extremize this. Take the derivative of that function, set it equal to 0, solve for the location of that. We don't know, you remember from calculus, we have no idea if that's a maximum or minimum. We often refer to it as kind of minimizing the function, but in fact that's incorrect. We're really just finding the peak, the inflection point, the maximum or minimum, not inflection, the maximum or minimum of that function. We can check to find out if it's a peak or a valley by taking another derivative. And if you recall, thinking about the concavity of that function. Is it concave up or concave down? Or I always forget which one's convex and concave, but the point being kind of like, are you sitting at the bottom of a valley or are you sitting at the top of a peak? And that'll tell you whether or not you're at a minimum or a maximum. These same conceptual ideas extend to functionals. It's just that the mathematical treatment is different and it's kind of complicated. It led, trying to solve these maximum problems led to a new branch of mathematics known as the calculus of variations. And the reason why the calculus of variations is important to us is because most of what we do in mechanics is minimizing an action principle. Is trying to say, what is the action here? Is it motion? Is it storing energy? Is it fluid flow? Is it some dynamical system that is moving over time? We want to write down what that action is. What's an action? An action is you take the kinetic energy and you take away the potential energy and you integrate that between two times. So I take a ball, throw it up in the air, catch the ball. Time 1 is going to be when I let go of it. Time 2 is going to be when I catch it. I can write down the kinetic energy at all points of time, and I can take away the potential energy at all points in time. Carrying out that integral is my action. The principle of least action says that the motion of that ball is going to be dictated by whichever action has the smallest value. So let's dig in to what I'm saying now. Let's put let's really kind of like dig into the math of what I just said there in words. So we're talking about the principle of least action, which is one of the most important principles in mechanics and in physics generally. And I'm going to repeat what I just said. And what I just said is that imagine I take a ball and I'm going to throw it to the other side of the room. So I take a ball. It starts out over here. I'm going to throw it. Over there. And what I've just drawn here is the actual path the ball is going to take. So we'll use blue to denote that actual path here. So the action, as I said, is going to be take the kinetic energy, we'll call the kinetic energy capital T, we'll call the potential energy capital V. So the action is denoted by capital S. And we say we're going to integrate over the difference between kinetic energy and potential energy over time from start to end. Now let's do this. Yeah, no, let's keep that. That's fine. The idea is kind of simple. The idea is to say, well, I just drew an arbitrary blue path there. Let me copy that. The idea is kind of simple. So I have 2 points. I'm going to take a ball, I'm going to throw it from here to there, and I can just write down whatever path I want in between those 2 things. So I could say, well, I could just look at like something like this, or I could do like, maybe my ball took some crazy path, I went like this, or maybe something that's just slightly longer. Those are all different paths. And for each of them, I can calculate an action. And an action is just a number, right? How do I know it's just a number? Well, I defined it as an energy, which is a scalar, minus a different energy, which is a scalar. Integrate over time, I'm doing a definite integral. My result, my action is just going to be a number. So I could kind of assign a number to all these different pathways. If I assign a number to all these different pathways, I can say, well, the actual path will be whatever number is the smallest. And that's the principle of least action. That's saying, if I just calculate, on average, the kinetic energy at every point in time, and I take away, on average, the potential energy at every point in time, and I calculate the action for an infinite number of paths between those 2 points, the true path, the actual path you observe, will be whichever action has the smallest value. So we can formalize this and do it a bit more mathematically by saying that I have some position, x, which depends on time. And I could start at time 1 and throw a ball up in the air and have it end, get over there at time 2. So what I want to do here. And I can draw in my actual pathway. We'll call the actual path that the ball takes x bar of t. And we'll say that, well, let's do this more formally. We'll say that my kinetic energy T is equal to 1/2 mv squared. V is what? V is the derivative of x bar with respect to T. And that's squared. 1/2 mv squared. We'll leave our potential energy as just kind of unknown for right now. We can definitely plug something in here, but it'll be more fun if I leave it unknown. Maybe not for you, but for me. Okay. So this is our action. And, well, it's not our action. This is our kinetic energy. This is our potential energy. Our action is going to be take S, the integral from T1 to T2 of our kinetic energy, 1/2 m take away our potential energy and integrate it over time. Conceptually, What we'd like to be able to do, which is going to be clearly impossible, is to just say, well, why don't we just write down every possible path, calculate the action, find the smallest, and then our problem is solved. Well, there's clearly an infinite number of different lines I could draw between these 2 points, and so calculating the action for every single path is going to be not possible. So what we would really like is to have a mathematical procedure that lets us find this action. Unfortunately, we just can't take a derivative of s with respect to, I guess, what, to find and set that equal to 0 like we would with calculus, because we don't have a function here that we're trying to minimize. And this part, I think, trips people up. And so I'm going to just take a second to tell you what I mean by this. So with ordinary calculus, we are drawing a line, x of t, and we're saying we're finding a point at which is the maximum, there is a maximum or minimum, right? We take our curve, x of t, we take a derivative of it, and we're finding a point. So how do I draw that? So I have something that's like x, t, maybe it does something, and I'm looking for this point, which is going to be a value, right? I take the derivative of this function, I take the set that equal to 0, I find this value, and what I'm finding is I can find the x location of that maximum or minimum. I can find the time at which that maximum minimum occurs, but what I'm looking for is a point. And now notice the difference here. Here's a problem in which what I'm looking for is a curve. I'm kind of looking at like a manifold of infinite numbers of curves, and I'm trying to find a curve that minimizes this function. It becomes more evident when I ask the question of like, what shape? If I want to create a slide, or if I roll a ball down the slide, the ball will get from the top to the bottom in the shortest amount of time. What shape should I design that slide to be? I'm clearly not looking for a number. I need a curve. I need like an actual physical, like a shape that I could draw and build. And that's kind of the difference between variational calculus, calculus variations, and ordinary calculus, is that we're not looking for a point. And in those 2 examples I gave you, the result was a curve. But I could also say, at any point in time, the shape of a fluttering flag should minimize the action on that fluttering flag. And so now what I'm looking for, if I wanted to find the shape of a flag, is I'm looking for a surface, right? I'm looking for a manifold, like a 2-dimensional surface that will minimize the action compared to all other possible 2-dimensional surfaces. And I can go into 3D as well. And you could say, like, I have a blob of Jello that I'm going to step on, and it's going to get squished and deform a lot. The shape of that blob of Jello is going to be 3-dimensional in nature. And so the thing I'm solving for would be a 3-dimensional shape. And so this is where you start to see the difference between kind of ordinary calculus, which is going to give you a point, and variational calculus, which is going to give you a function as a result of minimizing the functional. So we need new tools. And those new tools involve a lot of the same ideas we've been working on, which is the conceptually what we're saying is, well, this is the true solution, which means if I take the true solution, which I don't know, and I add to it a small other function, then the action of that additional curve that I just found should be larger than the actual action of my what I'm looking for. Let me say that again, because I feel like I might have confused. We'll deal with this one in red. So I can say, this is my shape, but let's take my curve, x bar of t, and let's add to it another function, but we'll add to it another function multiplied by a really small number. So we're kind of barely perturbing our actual solution. So we're like, I'm going to draw it exaggerated. I'm going to say it looks like this. But you could imagine that being like infinitesimally close to the actual curve. Okay, so my red curve is different than my blue curve. My red curve is not the actual path that the ball takes. We'll call my red curve x of t. And at any point in time, there's going to be a difference between those two curves. Actually, I'm going to draw that in a different color. At any point in time, there's going to be a difference between those two curves. Oh gosh, that's not good. And that difference we'll call eta. I think students, so let me do one more thing. I'll say this lets us define our x of t as being our original function, which we don't know, but we know that our original function, we're just saying our original function is the solution. We don't know it, but we're going to call it the solution. So x bar is the answer. We just don't know it yet. So our guess, our perturbed function x, is our answer, x bar, plus some other function that depends on t, eta, which has been multiplied by our favorite, epsilon. In this case, epsilon is just an arbitrary small number. It's what's referred to as, based on what we know from the last section, as a perturbation of our actual function. We're going to take our actual function and perturb it a little bit. I think students typically get confused here because it's a little conceptual. I've got x of t, I've got x bar of t. Imagine like that x bar of t is like a parabola, and the eta of t is like we can think of it like in the sense of almost like a Fourier series. Like imagine eta of t is adding like sine of t to our parabola. So we have like our curve, but then we have like a little bit of a wiggle to our curve. But then we just say that we're going to add a really tiny wiggle. So we're going to take our sine of t or our cosine of t, whatever function you like, that's going to be our eta, multiply it by a really small number. So that way we have our original function. We're going to add to it some new function, something that who knows what it does, but it's different, multiplied by a really small number. Okay, I've been talking for a while. How are we feeling? What questions do you have for me so far before I dig in?
So is the original function x of t, or is it x dash of t?
So we are trying to find the curve that minimizes the action between T1 and T2 for a ball thrown up in the air. That curve is the blue curve denoted by x bar of t. We don't know what it is. I've drawn it. We just know that some curve exists that minimizes that action, right? There's got to be, if I have an infinite number of actions I could calculate, all those actions are just literally numbers. One number is going to be the smallest, and we're going to take that one, and we're going to call that action that minimizes the shape that minimizes the action. We're going to call that shape x bar of t, and our goal is to find it. So x bar of t is the actual trajectory that we expect the ball to take, and what we do is, in order to find it, is we say, well, let's consider some arbitrary curve that is the real solution perturbed a little bit. We know that the action for x of t has to be larger than the action for x bar of t. Because we've said x bar of t is the solution. So any other action has to be larger. Does that answer your question?
Yeah, thank you.
Other question?
I got one question. So the way we define the problem about like throwing a ball, I felt like x was vector, but it seems in this graph it seems it's scalar.
No, I think x should be a vector. Epsilon is a scalar, and our action is a scalar, and obviously the kinetic and potential energies are scalars. But
okay, so x and x bar and eta should be all vector.
correct.
Okay, thanks, got it.
I know you said this already, but could you briefly give an example of or clarify what you mean by action?
An action is a very specific definition, and an action is the difference between kinetic and potential energy integrated over time.
Okay. And so in this example, you could sort of, okay, never mind. I think I follow.
So it's a very specific thing. So this is our kinetic energy. This is our potential energy. I take the difference. I integrate between two time, initial time and final time, and that is my action.
Okay, thanks.
Which is a fundamental physical quantity in the same way that kinetic and potential energy are.
What does, like, I guess, like, what does action mean, like, conceptually? Like, beyond the mathematical, like, definition here?
That's a good question. I'm gonna make up what I think of as the answer, and so this might not be what you find in Wikipedia or something, but I guess I would say I think of it as kind of like the almost like the I feel like that's not a helpful thing. I don't know what to say. It's I mean, I guess in my head I think of it as like kind of like the residual or like the kind of the not the energy of motion, but kind of like the residual energy of motion. So you're kind of like you have some dynamical system that is moving, and you're kind of comparing like how is it moving relative to like how much it would cost to use up any energy that is left in the system, and you're kind of always looking at that between like a beginning and an end point. So I don't know if that's like a good word for it. I always think of it as being kind of like a residual in a sense. But I hesitate to say that because I feel like it's probably not I don't know that brings any other physical clarity to the situation. I'm sure there's a better definition in the physics world that I'm drawing short on at the moment.
Is it valid to say that it's analogous to following the path of least resistance?
I mean, that's
In a sense.
a different way of kind of restating the principle of least action, but I don't know if it helps us get at what the conceptual idea of an action is. I think you're like the path of least resistance is kind of like a subset of the path as the principle of least action. The principle of minimal potential energy is a subset of the principle of least action. Because if you say, well, there's no kinetic energy, then I'm just left minimizing the potential energy, and that's the principle of minimal potential energy, which tells you what the shape of your kind of deformed object in static equilibrium is. This is kind of the bigger all-encompassing one, which accounts for kind of the energy stored in the thing and the energy expended by motion. I
Gotcha.
don't know if I have a good conceptual definition, but I will find one. Try to either come back to it. Yeah, that's a good question. Does everybody understand the blue and the red curve? Because this is kind of the crucial part. Because everything else that we're going to do right now, we're going to kind of do some turn the crank mathematics. But if you don't understand the idea of adding a small perturbation to the actual solution, which we don't know, and then using that to help us find the actual solution, if this image doesn't make sense, or the ability to translate this image into that equation doesn't make sense, we should chat about it, because this is kind of like the tricky conceptual part for the moment.
So I get like this whole concept, I guess just like on the picture itself, I don't understand why the red curve and the blue curve are not equidistant throughout the whole curve. You know, why it's not always a difference of like why it's not always the same difference.
Sure.
If that makes sense.
So there's 2 points I want to make. One of them I haven't said yet, and the other one is maybe conceptually a little not obvious. The first point is we should be able, if the blue curve is the curve that minimizes the action, then we should be able to draw any other curve we want in between those 2 points, and it should have a larger action than the blue curve. And so therefore, we should be able to place no restrictions on eta of t. We should be able to draw eta of t to be whatever we want. We can have it be big to have a big difference between x bar at the beginning and a small difference at the end. We can have it be almost exactly the same, except like spike here and then come back. The idea is to say that any curve eta is going to have a larger action, any curve eta that's added to x bar is going to have a larger action than x bar. The second point of why would the red dash curve not have like the same distance as I march across from T1 to T2 is a bit more subtle, and I haven't said this, but one of the only restrictions on eta is that eta has to start and stop at the same points as the blue curve. It wouldn't be fair for me to say, I want to figure out what motion my pen is going to take when I throw it up in the air and I catch it. If I then say, allow it to predict a motion in which I throw this thing from down here, or I throw this thing from up here, it has to start and end at the same point. Otherwise, we're not comparing kind of two similar things. And so if you think about these two curves starting and stopping at the same point, then it becomes pretty clear that there's no curve except x bar that would allow you to go from T1 to T2 and have the same difference between them at any point. Because if I want something like this, but then this thing would have to kind of bend to here to meet that criteria of starting at T1. So it's actually not possible to have eta of t have like an equidistant value away from x bar of t because we require it to meet at t1 and t2. And we require it to meet for very, very fundamental reasons. Like if I take a sheet of paper and I compress it between my hands and I say, what's the shape of that sheet of paper? It wouldn't do you any good if one of the ends of the sheet of paper was up here and my hand was down here. That's not a solution. I have to make sure that the end of my sheet of paper is exactly where I say it's going to be. Otherwise, I'm solving a different problem. Does that help answer your question?
Yes, a lot. Thank you.
Okay. So let's take our action over here. Oops, I'm sorry. I wanted to call our action that we've been writing. I wanted to call this action S bar because that's the one that corresponds to the actual X bar. And so then I want to come down here and draw out S. And S is going to correspond to X, which is this quantity up here. Okay. So I'm going to still integrate from the same bounds, T1 to T2. I'm still integrating mass over 2. But now, this quantity here, which was dx bar by dt squared, becomes dx bar by dt plus epsilon, which is a scalar, times d eta by dt. And now that whole thing is squared. And now I'm going to take away my potential energy, which I didn't really tell you anything about, but we'll leave that potential energy as just x bar plus epsilon eta. And we're integrating over t. How are we feeling? Make sense? All we did is insert that into our action. Now we can do a little math to simplify things. So what do we want to do? Well, we can certainly expand this thing. So what do I want to say here? dx sorry. I gotta draw this down here. Let's see here. dx dt squared is equal to dx bar. So just basically foiling what's inside the parentheses there. Wow, I can't write today, huh? Sorry. Let's try to clean things up. And now you can already see some of like the language we've been using start to come back into play here. So for instance, pretty clearly, this first term does not depend on epsilon. This second term is of order epsilon. And this third term is of order epsilon squared. Just like how when you, in ordinary calculus, find the extremum of a function by taking the first derivative and setting it equal to 0. In the calculus of variations, you find the function that minimizes the functional at first order in that perturbation, which means that we're going to mainly concern ourselves with these two terms, and these are our higher order terms. Second order and eta, if you will. Okay. So we also need to make some sense of this quantity. Let's see what I want to use. Yeah, we also need to make some sense of this quantity here. And so if I come down here, what do I do when I have something that looks like this? I have some functional. I don't really know what it is. It depends on x bar plus a small thing. What do I do when I have some complicated thing that contains this kind of perturbed quantity? I take a Taylor series expansion. Same as what we've been doing up until this point. I Taylor series expand around what point? I Taylor series expand around the perturbation being 0, so around eta being 0. And so I'm looking at v of x bar plus epsilon eta v prime of x bar plus epsilon squared eta squared over 2 times v double prime of x bar plus, and so on and so forth. And once again, I see the appearance of an order epsilon term. I see the appearance of an order epsilon squared term, and I stopped, but you can keep going. And now I can insert this quantity and this quantity back into here, into my action. So we'll come down here, go to our action. And I can say that my action is the integral from T1 to T2 of this. I'm writing this a specific way, and you'll see why in just a second. And the reason why I wrote this a certain way is because it becomes very clear that these first two terms, when integrated over the same bounds here, are exactly equivalent to the true action of the minimum path here. So I recover this, when integrated, is actually S bar. And so what I can do is, I can write this one other way, and I can say that, well, if I just move this to the other side of the equation and I say, take my true action, take away my pretend action where I just perturbed the true action. If this difference is 0, then I have found X bar. That's a pretty trivial statement, and yet I'm sure it's confusing, which I guess is a weird contradiction. But if the action of X bar, which we know solves the problem, minus the action of our perturbed situation is 0, then we know that our guess for the perturbed situation is equal to the actual solution, and we found the curve X that minimizes the action for our system. This is what's referred to as the first variation. It's denoted with a delta and an S. And we'll also probably move away from the notation that we've been using of this epsilon eta eventually, just to kind of match up our notation with what's more commonly seen in the literature. But this right here, we're interested in a change in the action, and we're interested in finding the change in the action when it is 0, because once we have done that, we have found our solution. This is what's called the first variation, because we're only considering order epsilon eta terms. If we considered order epsilon squared eta squared terms, that would be the second variation. Why do you want to determine first variation? The first variation tells you the equilibrium solution. The second variation tells you the stability of equilibrium. Think back to ordinary calculus. The first derivative of your function with respect to your independent variable set equal to 0 tells you the location of the extremum. The second derivative tells you if that extremum is concave or convex. It tells you the stability of that point, if you will. If you put a ball on top of that curve, is it going to roll down or is it going to stay where it is? Okay, so we have set up the problem, but I want to take a break before we solve it. And I want to answer any questions you might have as we do that. So what questions do you have for me? Nothing? All right, why don't we all take like a 5-minute break. And in that time, if you think of any questions, feel free to shout them out. I'll just be standing here. Otherwise, I'll see you in like 5 or 6 minutes or so.
Professor?
Yeah.
I just missed it, but what's the order of epsilon square, eta square is written with the eta in that term?
Yeah, it's written that way because typically what people consider is if you like do this work in the field of mechanics, you won't often see epsilon eta. What you'll typically see is kind of like people will write this. They will write what do I want to write this in on? They'll write this. and they'll kind of, this whole quantity will get lumped into here. And then they will write to order delta of x, or to order delta squared of x, delta cubed of x, depending on which order they're, of the variation they're taking. And so you'll typically see this notation, and I'll show this notation more formally for you at some point, but not today. But it's because we're basically saying, what's the magnitude of the perturbation? And the perturbation is the product of the function that you're adding and the small number you're multiplying it by. And so we're saying, what's the order of the perturbation? At first order, it'll be epsilon eta. At second order, it'll be epsilon eta squared, epsilon squared eta squared. And so it's really, you're kind of saying, what order is the perturbation at? And the perturbation here is going to be a perturbation to a function, or it might be something bigger than that.
Okay, I see. So we're also taking the order of the perturbation itself in addition to the epsilon.
Yeah, the epsilon is like the small number that multiplies the function. Together, that quantity of the small thing multiplying the arbitrary function is how we perturbed the original function.
Okay, I see.
You'll typically see it more like order delta squared, order delta cubed. But I just haven't, I don't introduce that notation right away because I find it simpler to think like add a function, multiply that function by a small thing, which is epsilon, which we're used to doing at this point, I think.
Yep.
In practice, when you actually have S bar minus S, are you able to get the actual function, or are you just sort of approach zero when you?
No, actually, you'll see like basically when we get back from the break that like variational calculus has like what feels like magic to it, where you basically like kind of do a simple trick and you just like get the, it just drops out of the simple conceptual trick. Now it doesn't mean it doesn't get complicated, but like there's a conceptual trick that allows us to basically actually ensure that we find the minimizing thing. Now that minimizing thing might not be X bar. More likely what it is in mechanics, more likely what you end up with after you do the variation is either something when you get here that you can solve numerically, or a differential equation that you could solve analytically. So the end result is not usually like, boom, there's X bar. Usually what you get is like, here's a differential equation for X bar. Now you can go do your perturbation methods or do your solving of it. But even if you don't really care about analytical solutions to interesting mechanics problems, if you're doing anything computationally, like find elements, find difference, anything where you're solving continuum mechanics problems, solid or fluid mechanics problems using commercial finite element software, computers have a really hard time if you just say like, here's a differential equation, solve this. The challenge for a computer is that you are giving them an equation that is what's referred to as the strong form equation. It says at every single point between T1 and T2, I need you to ensure that all these derivatives add up to exactly zero. And you do something with a computer, nothing ever adds up to zero. It's really hard to do that. And so what you usually use in computational mechanics is not the strong form, which is the differential equation that we're used to. It's the weak form. And the weak form is the differential equation integrated over some bounds. And the reason why that's better is because when you integrate something, you say, I just need the average of this integral to be 0. So then you don't have the same restriction, kind of strong restriction that point-wise everything has to be 0. Over this domain, everything has to average out to 0. That's easier for computers to handle. And what we will, I think, talk about, I forget if we go through it or not, is that this variational approach is identical to the approach you use for deriving the weak form. Like they're just the exact same. So if you want to derive the weak form for the equations you're going to solve computationally, exactly the same. If you want to derive governing equations that you want to solve analytically or that you want to perturb, this approach. So it's really powerful in that sense. But yeah, you'll find that what you usually get out of this is a differential equation that you then have to go and solve. Should we get back to it? So we're interested in ds equals 0. That's the first variation. So let's write out ds equals 0. I'm going to try to stand over here. My iPad is dying, so let's see what I can do. Or maybe what if I sit down? Magical. Yes. Sorry, people in the classroom will be less animated. Okay, so what we need to find is dx, and we need to set ds equals 0. So let's see here. So let's draw some stuff. Oops, that's terrible. Okay, so well, we need to set ds equal to 0. So what's ds? Well, ds is going to be s, and as long as we remove this s bar here. So we end up with okay. I think that's right. Did I do that? I have the signs right here, so I would take S. So I need to take yeah, I think that's fine. I think it doesn't matter. Okay. So here's where it gets interesting, and here's where I make that point of kind of saying that this goes back to, I think, Alita's question, which is like kind of more conceptually, like what's the nature of eta of t? Like, why is it not continuously different? Why is it, how do you pick the shape of it? And it gets to that point that I said, eta of t is arbitrary. It's completely arbitrary. So why is that important? And it's important because if I could factor out eta, then I could get something that looks like this. Integral t1 to t2 is equal to, let's just make up a thing. Let's call it capital A times eta integrated over t. So if I could factor out eta, So I have eta times a integrated over time is 0. And if I tell you that eta can be any arbitrary thing, and it's not 0. If it's 0, it's not useful. If it's 0, we have the problem solved. So eta is not 0, and it can be any arbitrary function that you could dream up. And I need the integral of a that multiplies eta to be equal to 0. Then I can just take a and set that equal to 0, because eta is arbitrary, and so it's going to be some number, but I need the product of a times eta to be 0. That means a should be equal to 0, and if a is equal to 0, then I've solved my problem. So that's the conceptual leap here. Eta is arbitrary. If I can factor this equation so that each term is multiplied by eta, pull out eta, then whatever is left on the inside has to be 0 to minimize that action. And the problem is this thing. We know stuff about eta. We know eta is arbitrary. We know eta has to be equal to x bar at these beginning and end points. We don't actually know that about eta dt. You can set a beam and say that the location of that beam has to be 0 at a wall, but it doesn't say anything about the slope of that beam. That's a separate condition. Those things can be unrelated. So we actually need to get rid of this derivative. And so the thing I want you to have in your head is, if I'm ever seeing the appearance of the derivative of my perturbation, I need to get rid of it. I need to get it into the form of something times eta, not something times d eta dt, or the second derivative of eta with respect to t. It needs to be this quantity needs to be changed to something times eta. And the way we do that, I'm actually gonna, let me just move that around, actually, sorry. I'll move that below. And here's the crucial step. Here's the crucial step. I can get rid of that derivative by integrating by parts. Okay, you probably have forgotten all about integration by parts, so let me remind you. Let's write this over here. And if you don't remember why this is a solution, we'll walk through it, but I kind of wanted to quickly just remind you. Integration by parts. Integration by parts, if you've forgotten, is basically the product rule backwards. What's the product rule? The product rule is if I take the derivative of, let's say dx by dt of u times v, then I get u dv dx plus v du dx. Integration by parts tells us that the integral of u dv is equal to the uv minus v, the integral of v du. this is one of those, if you kind of take nothing else away from this class, I want you to, like, if I could list the things that are important, one of them would be, when in doubt, try to do a Taylor series expansion of the function that you're staring at. The second thing would be, what if I integrate by parts? And this is kind of closely tied into things about utilizing the Green's theorem, divergence theorem, Stokes theorem, those kind of, all those theorems, they're all doing very similar things about integrals and boundaries and surfaces. These are kind of some of the main takeaways I want you to have. But for right now, I want to focus on integration by parts here. And so let's remember what we need to do. We need to take this thing that I've underlined, and we need to get rid of d eta dt. So let's think about this in the sense of integration by parts. Let me take this quantity and bring it over here. And let's say, okay, well, what am I referring to? Well, I have this integral of mass times dx bar dt times eta times d eta dt. And if it helps you, then this is all integrated over dt. Like this is kind of like your u and your dv. So this is equal to eta times, sorry, epsilon times eta times mass dx bar dt minus epsilon. I'm going to pull out epsilon. I'm going to pull out mass as the integral of eta times d by dt of dx bar dt. This part's crucial, and so take a second and see that you can verify this on your own. Are we okay with this? This is really important. So
Can you say again what you defined as U and V?
Sure, like you could call like call this U. You could call this dV. And so then this would be V. This would be U. This would, I pulled out some stuff here. So this would be du. Oh, I totally messed up over here. That's supposed to be. Sorry, everyone. Okay, so then this is like du. And I've just pulled out this m because it doesn't depend on t, so the derivative doesn't matter. And then this would be v. And I've kind of pulled out epsilon because it's not going to matter in the integral. Both of these are scalars. Does that help?
Yeah, thanks.
Now I kind of skipped something here, but it's actually kind of important. And what I skipped is, when you usually see integration by parts, you see that kind of generic integral of u dv is equal to uv times the integral of v du. But this is true for definite integrals too. So I can put the definite integrals here. Doesn't change too much over here. However, what it does change is that this whole thing should be evaluated between T1 and T2. So it's like, it is truly a definite integral. Same thing applies. I just left it out at first to kind of match that notation, but it's the same. But that's actually going to be a really crucial and important step here. Okay, so we're almost done. So now let's go back to our action ds. And,
Sorry, I have a quick question. Where did the extra dt come from at the very end?
are you referring to this or this?
The second one, like the very last one, the dt by itself. Yeah.
Yeah, the dt by itself is just, that's the domain that we're integrating over. So we integrated, so that's gone here, but we're integrating over this domain here. And so this has been extended from kind of calculus, where you have you're thinking about derivatives of functions, to variational calculus, where you're thinking about functionals. And so you end up with like x is derivative, like the du is kind of in here, but then you're still actually integrating over a time domain here. So it's kind of the difference between what we're used to with calculus versus now we have calculus of functionals, which means that we have functions of variables, and so we're still integrating over this time domain here.
Okay, thank you.
Okay, so let's get back to what we're after, which is now we can go back to our first variation. And our first variation becomes, well, this quantity here. So we're going to have m, did I lose an epsilon? Yeah, I did. Oh, let me write this in the same order. Sorry. It's going to be like epsilon eta m dx bar dt, evaluated from T1 to T2. We're going to have the other term, which is going to be minus epsilon times m times the integral of the second derivative times eta integrated over t from T1 to T2. And then I have to also take away epsilon times the integral of T1 to T2 of eta of v x bar times eta dt. Now remember what this means. I'm going to come over here and edit this a little bit. So eta here, I just want to be explicitly clear. Eta depends on t. So when I'm inserting T1 and T2 into here and evaluating, remember that eta is the difference between x bar and x at a time t. So it's this difference, this purple line. And we know that at T1, eta at T1 is exactly 0. And eta at T2 is exactly 0. And so if eta at T1 and eta at T2 is exactly equal to 0, I'll write that out. then this entire quantity goes away. And now look at what we're left with. The variation, the first variation in our action is equal to two quantities. I guess I kind of can keep that like that for now. Is equal to two quantities that both depend on eta. And I can pull out epsilon as well, because epsilon is an arbitrary small number that multiplies eta, which means I can come back down here and say that the first variation of our action is going to be equal to the integral from t1 to t2 of negative m And now here's the thing. If you go back to what I said up here, if I'm requiring that the integral of a times eta is equal to 0, and eta is arbitrary, so no matter what value I choose for eta, what function I choose for eta, what value I choose for epsilon, no matter what I choose, that's a number, it's arbitrary, and this action has to be 0 for it to be a first variation. The only way that's possible is if the thing that multiplies eta is 0. So that allows us to say I have something that's multiplying eta. Therefore, the thing that multiplies eta has to be equal to 0. And if you remember, what's the derivative of a potential energy? What's the derivative of energy, I guess? With respect.
Is it power?
No, that would be if you multiply it by time. It is a force, which means that we've just done a lot of work. If this is a force, and this is acceleration, then we just found that F equals ma. We found Newton's second law by assuming an action principle needs to be minimized. We found our governing equation. And like I was talking about during the break, we didn't get x bar. We want x bar, we didn't get it. But what we now have is the governing equation to solve for x bar. So it's a differential equation. It's going to be a second order. We've done this before. We've solved this.
How did v x bar turn into v prime x bar again?
How did that happen? Where did the v prime come from? I definitely feel like I left that out somewhere. Here it is. Nope, I just missed it. It was always, so it's v prime because of the series expansion on v. So
Okay. So your first rewrite of ds should be v
I
prime.
missed one here. Yes, thank you. So on the one hand, this is kind of lovely because we just went from a completely different conceptual starting point and arrived at something that is like ground truth fundamental to us that we understand. But this can be applied to a whole range of arbitrary problems, maximizing or minimizing anything. What's the shortest distance between 2 points? What's the shortest distance between 2 points on a sphere? What's the shortest distance between 2 points on an ellipse? What is the shape that minimizes the total potential energy when you load this structure? You can use this same process to derive the governing equations that you then want to solve. Or if you're interested in finite element modeling, what you have here is your function and your test function. The thing that you're telling your computational software is this arbitrary test function, and you need to just ensure that this integral is always 0. So you have the ability to do computational mechanics because you now have derived the weak form. Or you can do analytical mechanics because you now have a governing differential equation, which you can then go off and do perturbation methods on, or other analytical techniques to solve this. And it's all based on this general principle that whatever action is the smallest, that will dictate the, in this case, pathway of the ball that we see. In another case, the shape of the slide that we should roll a ball down, the shape of a soap film, the shape of my wrinkly skin, like the shape of a huge range of problems in mechanics. And it's all based on this simple principle of least action, simple conceptually. And we're going to kind of use this going forward to solve a variety of problems using variational calculus. And so at the beginning of next class, next week, what we will do is derive another equation that should be really familiar to you. And if it's not, that's okay. And then we'll start doing some simple problems, kind of like the fun intro to calculus variation problems that we encounter. And then we'll talk about some other things that'll be useful in this context. And so we have a few minutes for questions if people have anything.
I guess, could you explain again, like conceptually, what us getting F equals MA means in relation to like our original like curve with the 2 endpoints and like finding the minimal value curve, basically?
Yeah, so if I was to say, I'm going to throw a ball up in the air and I'm going to catch it, and I want to know the trajectory of that ball as a function of time. What we did at the beginning, that's exactly what we did on the first day of class. And what we did on the first day of class is we said, well, F equals MA, and so therefore we can solve for the trajectory based on F equals MA. Where does F equals MA come from? Well, it's just been kind of written into our brain from years and years of physics. However, what this approach is saying is that if we just think, can I write down the kinetic energy? Can I write down the potential energy? If so, I have an action that I can calculate. And by making one assumption, which is that things tend to minimize action, I can derive that equation. So is it useful in this case? No, obviously we know F equals MA, and obviously we know we could have sat down and said F equals MA, so let's just do that to solve it. But here we derive the equation without needing to know anything. We just need to say, okay, well, I know that, I know one principle, which is that action should be at a minimum in all the things that are happening in the universe. Whatever is happening should be minimizing the difference between kinetic energy and potential energy at that time. And so if it's kind of like we didn't need to know F equals MA to solve this problem. All we needed to know is that things tend to minimize their action. And in this case, what we ended up solving for was an equation that's incredibly familiar to us. We can use this problem to solve for the equation of the elastica, to solve for the equation of a soap bubble, to solve for the equation of equations of geodesics, with shortest distances of curves on arbitrary manifolds. And here's our kind of way of saying, well, if we can use it to solve those other things, shouldn't we be able to derive kind of one of the most important equations in classical mechanics from that same approach? And so that's the kind of point of today's lecture. It is to say, you can find the governing equation you need to solve just by stating that we require the action to be a minimum.
Okay, that makes sense. Thank you.
Why did you set the bracketed term equal to 0 and not eta t equal to 0? Just intuitively.
Can you repeat that again? It was just breaking up real quick. What did I set what to 0?
Why aren't we intuitively looking back at how we graphed the problem? Aren't we trying to find eta t is equal to 0, not the why did we set the bracketed term equal to 0?
No. Yeah, great point. So so eta t is just the difference between my pretend curve and the real solution.
Right.
And so I could take any infinite number of choices for eta of t. And I kind of drew those over here. I could take any arbitrary choice. And for each of these, at some point in time, I can calculate kind of eta, the difference between that curve and my pretend guess at the curve. So the point is, no matter what I choose for eta, any arbitrary function that I put in there, no matter what I choose, if x bar is actually the pathway that minimizes the action, then the difference between s bar and s, which is this first variation, has to be exactly equal to 0. And so what I'm left with is an integral of the product of something times something that is not 0. And if I need the product of something that's not 0 times something that we don't know to be equal to 0, then the only way that's possible is if the thing we don't know is equal to 0.
Why do we know, sorry, maybe this is repeating it, but why do we know that eta t is not 0?
Because if eta t was 0, then we have x bar, and then we don't have to solve the problem because we know the answer. We're assuming that we don't actually know x bar. We're going to say x bar exists. I'm going to add to x bar some perturbed solution that is not 0. Because if I add 0 to it, then I don't have a problem to solve because I don't know x bar.
Okay.
But what I've done is say, well, I can add to it some small perturbation to that thing, which should be finite, but small.
Okay.
Therefore, what I'm doing is saying that I have the product of something that is arbitrary, any value would work, times something that's we don't know. Therefore, if the product of those things has to be 0, then the thing inside the brackets has to be 0. Because this one is just arbitrary. It's something we can just arbitrarily choose. And oftentimes you just kind of are just pretending, you're saying it exists. There's some function that would perturb our actual solution.
Gotcha.
Professor, I think maybe this is a stupid question, but it seems to me that the derived from the original equation, we only have f equals to minus ma. But I don't know if it is because of the vector calculation. Yeah.
I think, let's see here. Did I screw up my signs? It's very likely that I screwed up my signs. It's not a stupid question. It's certainly a good one. I most likely screwed up my signs somewhere in here. And where is the question? Yeah, I don't know. So I have a feeling I messed up my signs somewhere. Minus v minus that plus. I'll have to go back and double check. Thanks for bringing that up. It does seem like we have a sign issue. Where I made that mistake is not obvious to me at the moment.
or maybe someone is put it up on the chat. Yeah.
Oh. Yeah. Thank you. Perfect. Thank you. Obviously, it's too long of a day, too long of a week. Perfect.
Yes. Yeah, thanks, Professor.
Thanks. Oh, not me. All right, this is the intro to a new section. We're going to be talking about this for a bit. Yeah, so if we have questions, we'll chat again on Tuesday, and then there's office hours next week as well, so we can talk about that. And in the meantime, good luck on the midterm, and hopefully next time we meet, the country is on the right path back to normalcy. Thanks, everyone.